Hello, Tensor friends. I got an interesting question here, which I've never really thought about. What is the difference between tensor algebra and linear algebra? Now, the question said tensor calculus, but I changed the word to algebra so we can compare apples and apples. Uh, it's the same answer. It is tensor algebra is the generalized form of linear algebra, just like tensor calculus was the generalized form of vector calculus. It's the same answer. Now, if you ask a mathematician, their answer has to be very precise. They're going to look about linear, the mappings and multilinear mappings, bada bing, all of that. I want to give you a practical example because that's the way I think. Okay, so what we're going to look at is the dot product and compare linear algebra and tensor algebra. Okay. So what I've got here is two column vectors the way they would write them in linear algebra. So they would say the vector A is 1, 2, and the vector B is 3, 4. Now I want to take the dot product of those, right? So I'm going to say A times B, cannot multiply matrices with incompatible dimensions. Okay, so we have a 2 by 1. We're trying to multiply that by 2 by 1. And you can't do that, right? So m times n is n times m can be multiplied together. So how do you do that in linear algebra? Well, you take what's called the transform. So you change A, which is a column vector, into a row vector. See that? And then you could multiply it by B, and you get an answer, a scalar, right? So you're mapping two vectors to the real numbers. And what you're actually doing is taking a vector and changing it into a covector. A transpose is a covector. I didn't know that all those years ago. And I was always very uncomfortable. Why do you have to do that? What does that mean? That's what you actually do. So this is a covector acting on a vector maps to the real numbers. Okay. So that's how it's done in linear algebra. Now let's go look at some tensor stuff. Okay, so we're going to derive the generalized form of the dot product in tensor algebra. Now we've done this before, but it's okay to review it. We have two vectors here, A and B. They're both written as a linear combination of their components and basis to vectors. And we're writing this in the summation notation, right? So when you have an upper and a lower index, it implies a summation. So in 2 dimensions, you'd have 2 of these, in 3 dimensions, 3 of these. All right. So let's take the dot product of those two things. So we would write it like this, dot this. We could pull the scalars out front, right? We're just left with the dot product of these two, the vectors, the basis vectors. Well, what is that? Well, we know what that is, don't we? That's the metric tensor, and here it is. So the dot product of A and B is equal to the tensor ij times the components of the two vectors. Okay. Now, most linear algebra is done in the Cartesian coordinate the system, and the metric tensor in Cartesian coordinates is given as the Kronecker delta ij. So if I equal j, then the Kronecker delta is equal to 1. If I does not equal j, then it's equal to 0. So there's only two choices, right? So as an example then, G11, so that's I equal j, equals G22, they both equal 1. And G12, G21, so the mixed off diagonal elements are 0. So the metric tensor in the Cartesian coordinate the system is the identity matrix, right? So that means that when we have these two vectors, I made them up, 1, 2, 3, 4, just like the ones we used. So the G11 is 1, and 1 times 3 is 3. G22 is 1, and 2 times 4 is 8. We get 11. That's what we got when we looked at it, the linear algebra, the method, okay? But this formula works in any coordinate system, Euclidean and non-Euclidean, all right? We just did the simple example. So let's do a really not simple example. Let's do one in a paraboloid. So this is the equation of a paraboloid, and we've done this before also. We parameterize the surface because we only want to look at surface coordinates with u and v. So we have these equations. We define a position vector. We take the first derivative of that with respect to u and v. We get our basis vectors. We use those basis vectors to find our metric tensor. So this is EU.EU, EU.EV, EV.EU, and EV.EV. So you notice right away, none of these are zero. None of them are, these two are alike because it's always symmetric about the diagonal. So these basis vectors, they're not orthogonal, they're not normal, they're not Euclidean. All right, they're totally something different. So let's go look at it on a graph. Okay, so I'm in Desmos.com 3D. Here is the equation of a paraboloid in 3D, right? Now, on this surface, we can define a point. And we do that by a parameterizations of a paraboloid is just a bunch of circles stacked together with different radiuses, right? So those are the transpose equations I'm using, and they are these three equations: the capital X, capital Y, capital Z. And what that does is A would be the radius of that circle, so I can make the circle larger or smaller. And T is theta, the angle from the center to the surface, okay? So it goes around and around and around. Now, on that surface, at that point, we can define a tangent plane. So this is the whole trick of Riemannian geometry. It's not a trick, it's the way it works, right? So you have a point on a surface, and at that point, you can define a tangent plane. And now in that tangent plane, I can define my basis vectors EU and EV. And you can see that first of all, you can see they're not orthonormal. They're not 9 degrees apart. They're not 1 unit long. They're just crazy. And they move all over the place. But they stay in that tangent plane. That's the point, right? So if I move the radius up and down, you can see it tilt. Do you see it tilt back and forth? And then when I move it, it changes everything about them. It changes their magnitude and direction. Okay. Now, at that point, in that tangent plane, I need to stress that a lot. We could define the metric tensor, right? So we got G11, G12, G21, G22. But I'll look at this point here. G11 is 16 and change. Now let's move this angle. Let's go back and look at it. Look at that. It's 22 and change. So that's what I'm saying, that you can only compare apples and apples by doing anything you're doing at that point in that tangent plane. So now we can define two vectors. So we got vector 1 and vector 2, and they have these coefficients, the scalars, just whatever they turned out to be, D1, D2, da, da, da. Okay. Now, the dot product of those two vectors is the multiplication of the scalars times the component of the metric, the tensor, right? So I've got all 4 of them here, and you see I get this weird number for the dot product, which it makes sense because they're different quadrants. So you are going to get a negative one, right? But once again, if I go back up here and change that point to a new point and go back and look at that, it's totally different than it was, right? So this is the generalized form of the dot. The product works in any coordinate system in any number of dimensions. Now, you said, well, what if I had a vector in this tangent plane and I wanted to take the inner product of it somewhere else, like over here? How do you do that? I don't know. That's above my pay grade. I don't think you can, but I don't know that for sure. Because everything, as far as I know, in Riemannian geometry, all the work I keep doing is all done at one point in a tangent plane. Okay? So I hope that answered your question. If it did not, let me know. See you later.